Alright, so this is the last lecture that we will need for finishing the topic of orbital maneuvers, and there will be no more makeup lectures that will be posted. So this is the very last lecture that you will need for to cover all the material for the finals. So in this lecture we will look at the final type of orbital maneuvers that are known as phasing maneuvers. Okay, so the corresponding notes for this topic is part 5 of the notes on orbital maneuvers that has been posted now on Sakai. So in this problem, the problem of phasing is described in figure 1 of part 5 on orbital maneuvers. And here the problem is the following. You have a circular orbit on which there are two spacecraft. Okay, so here's the focus, and let me use this as a reference line. And there are two spacecraft, S2 and S1, both on the same circular orbit. And I'm going to call S1 here as the chasing spacecraft, so chaser, and S2 as a target. Okay. As you can see, the spacecraft S2 leads spacecraft S1 by a phase angle beta. Okay, so beta is a phase angle, and S2 is leading. The objective of this maneuver is simple enough. Okay, S1 is the one that is chasing, so we need to do something to S1 so that it rendezvous with S2 at point A. Alright, so this point A is where the rendezvous takes place between S1 and S2. Alright, so we need to change the orbit of S1 so that it comes and meets S2 at point A. Alright, so the way to do this is, well, there are two ways, at least two ways of doing this. And the first way is the following. What we will do is we will transfer the spacecraft S1 into what is known as a higher orbit. Okay, so I'm going to transfer this spacecraft into this dotted orbit, okay, which is higher than this original orbit. So the original orbit is OI, and I'm going to call this transfer orbit OT. Okay, so what has happened here? Well, since OI is a circular orbit, OT, the transfer orbit, is an elliptical orbit whose periapsis is FA and the apoapsis is this right here, FB. Okay, if you may. Alright, so what has happened is, because of the fact that spacecraft S1 has been moved to OT, its period is now different from that of S2. Alright, and this OT, which is the higher orbit, is designed in such a manner that after a few rotations, so after a few go-arounds of S1 on OT, by design what will happen is that at some point in the future, both S1 and S2 will close out this phase angle beta and meet simultaneously at point A. Okay, so when that happens, the spacecraft S1 will be transferred back from OT to OI. Okay, so again, this is a two burn maneuver. Okay, and both the burns, as you can see, take place at point A. The first burn at point A transfers S1 from OI to OT. Okay, and the second burn, delta V2, also takes place at point A, and it transfers the spacecraft S1 back from OT to OI. Okay, so both these burns, as you can see, because of the symmetry of this process, are going to be identical in magnitude. Okay, so they are both going to be equal, and so the total delta V is going to be 2 times delta V1 or 2 times delta V2, whatever you like. Okay, so let us see how we can design this transfer orbit, this higher transfer orbit, okay, OT, such that after a few rotations or after a few circuits of S1 on OT, it meets S2 at point A. Right, so what we will do next is look at the analysis of how to complete this phasing maneuver. So remember, our objective is to design OT such that a rendezvous takes place at point A, right? So as far as the initial orbit is concerned, OI, we know that the speed on the initial orbit VI is square root mu over R, where R is the radius of the initial orbit OI. Alright, so let the period of the transfer orbit PT be let the period be PT of the transfer orbit. Okay, so this is the unknown that we are looking for. We must design it such that a rendezvous does occur. All right, so here's what we are going to say, that let the spacecraft S1, see S1 is right here, and it meets S2 at the same point, right? So what we are going to assume is that let S1 meet S2 at point A after K orbits on the transfer orbit OT. So let rendezvous occur after K go-arounds, K orbits of OT. Okay. So what is the amount of time it takes for the rendezvous to take place? The delta T, total time, wait time, is K orbits per orbit is time pt, right? So that is the amount of time it takes for the rendezvous to occur. Okay, this is equation 3 in the notes. Now, the question is the following. How much angle has S1 covered during this time? Well, S1 has covered K orbits, right? So in terms of radians, S1 has covered 2 pi K, or K times 2 pi. That is the angle that S1 has covered, right? But how much angle has S2 covered during the time, waiting time? So angle covered by S2 during wait. All right. Now remember, at the end of this waiting time, the rendezvous occurs at point A, right? So what we know is that after delta T wait, S2 is at point A. Okay, so what is the angle that it has covered? Well, it must cover first of all this remaining angle, right? So that angle is 2 pi minus beta. And to make things general, we are going to say that in addition to that angle that it must cover to get to point A, it has covered an additional q orbits. Okay, so per orbit it covers 2 pi. So this is the additional q orbits that S2 has covered in the time that S1 has covered k orbits on OT. Okay, so this is the distance, the angular distance that S2 has moved. Now, what is the angular speed of S2 on the orbit that it is on? So the angular speed of S2 is, we know, is the mean motion, and it is on the initial orbit Ni. So this is nothing but 2 pi over pi. Alright, so here we have the time it takes for the maneuver to complete. This is the distance, angular distance that is covered over that time, and this is the speed. So we know that distance is equal to time times speed, because the speed is a constant, right? This is OI is a circular orbit. So we have the distance 2 pi minus beta plus 2 pi q is equal to the speed pi times the time pt. Okay, so this is the governing equation that we have, and is equation number 6 on page 3 of the notes. Okay, now note that k and q are both integers. Okay, that is absolutely crucial to note here, that k and q are integers because they represent full orbits. Okay, so if if somehow you get that k is equal to 1.7 or q is equal to 2.3, there is something wrong, right? And we are talking about full orbits. So, but what we are looking for here is pt, right? That is the period of the transfer orbit that we are trying to determine. So these are integers, but they will be input as design parameters. Okay, so both k and q are user defined inputs. The user will decide how many orbits must S1 cover on OT before it meets S2 at point A. Okay? And during that same time, how many additional orbits Q must S2 cover on OI over and above this phase angle that must be closed out. Okay, so we can solve this equation for PT to get that. You rearrange the terms here to get 2 pi q plus 1 minus beta over k times ni. Okay, this is the solution for PT. And once you have PT, then of course, from Kepler's third law you get the semi-major axis, and that is going to be mu pt square over 4 pi square 1/3. Now, one of the important questions here is, are k and q allowed to be arbitrary, right? Well, the answer to that question is that one of them at least is allowed to be arbitrary. Okay, so let us see what the constraint is between k and q. Well, the first constraint obviously is that both of them are integers, right? So we must at all times satisfy that minimum requirement that they must both be integers, which means that the minimum value for both of them is 1. Right? So k and q are integers, which implies k min and q min. Well, k min is 1. Okay, that's the minimum number of orbits that S1 must cover, but q min can be 0 because in the time, this is just hypothetical, in the time that one orbit on OT is covered, we are going to say that the spacecraft S2 covers only the phase angle, okay, and no additional angles. So q min can be 0. Okay, we will see if that does indeed hold true, but that's one constraint we have right away. Now here's the other constraint. If you look at equation 6, okay, so the equation 6 and the RHS of equation 6, we have on the right hand side of equation 6 ni, which is the speed, times the time k times pt. But ni we know is 2 pi over pi k times pt. Now, in the picture that you see in the top right, pt, which is the period of the transfer orbit, is greater than the period of the initial orbit because the transfer orbit is bigger than the initial orbit. Okay, so pt is greater than pi for the higher transfer on the higher orbit. Okay, so what that tells us is that pt over pi is greater than 1. Now if I put this over here, I get that RHS of 6 is equal to k times 2 pi k times pt over pi, but pt over pi is greater than 1, so this is 2 pi k times greater than 1, and therefore I get that the right hand side of equation 6 is greater than 2 pi times k. Okay, so keep that in mind and return to equation 6 now. Okay. Equation 6 was the following. Distance equal to speed times time, but we've just shown that right hand side, which is this term, is greater than 2 pi k. Okay, so what we get as a result is that we get that 1 minus beta over 2 pi divided throughout by 2 pi plus q is greater than k, and that gives me that q is greater than k minus 1 plus beta over 2 pi. This is the constraint between k and q, okay, for this higher orbit transfer. Alright, so k is an integer and q is also an integer, right? So k is an integer. What about this guy? See, beta is always a number between 0 and 2 pi, right? So beta over 2 pi is always greater than 0 and it is always strictly less than 1. Okay, so q, let me draw the real line here just to get an idea. Here's k, this is k minus 1, and then I add this little phase angle to it, so this is k minus 1 plus beta over 2 pi between 0 and 1. Okay, so what we are saying is that q must be greater than this number, and since it must also be an integer, therefore q, the minimum value of q is right here, right? This is the range for q, and the minimum integer value it takes is k, right, in that range, in that feasible range. So that tells me that q min is equal to k. Therefore, for this phasing maneuver involving higher orbit phasing, we have the following constraints. K, Q must both be integers. K min is equal to 1, of course. At least one orbit is needed on the transfer ellipse. And Q min, we just found, is equal to K. These are the constraints. So Q can actually be, K plus 1 to K and K plus 2 and so on. And you are free to pick Q and K so long as you satisfy these constraints. Alright. So let us, what we will do next is take equation number 7, which was the expression for the period of the transfer ellipse. Okay, and in that expression we will do the special case in which Q is equal to Q min and is equal to K. Okay, so what we are saying is the number of orbits that S1 does on OT is the same number of additional orbits that S2 does on OI after it has covered that angle 2 pi minus beta. Okay, so when you plug in Q is equal to K in equation 7, you get that PT corresponding to Q equal to K equals 2 pi K plus 1 minus beta over Ni K, and this is equal to 2 pi over Ni, which is nothing but Pi, plus 2 pi minus beta over ni k. Okay, so the final answer here is that, let me just rewrite this equation. So the final answer is that pt is pi, which is 2 pi over ni, plus 2 pi minus beta over ni k. This is equation 11 in your notes. Alright. So basically this is all there is to the design of the phasing transfer orbit. Right? We found the period, and that's all we need to know. And what is left is to compute the delta V that is going to be needed to complete this maneuver. Alright, so all we need now is the delta V, and we have already seen that the delta V is 2 times delta V1, right? And that is, so 2 times delta V1, which is the delta V needed to transfer S1 from OI to OT. So the speed on OT from vis viva is 2 mu over r, but r at that point is cap r at point A, minus mu over at. Right? That's the speed on OT at point A. We already have at from the period using Kepler's third, right? We already derived that, minus vi, which is mu over r. That's the speed on OI. And that's it, right? That's the expression for the total delta V that is needed. So what we have done so far is we have looked at a particular type of a phasing maneuver, okay? And the details of the problem that we have looked at is that the chasing spacecraft S1 is lagging behind the target spacecraft by an angle beta, and they are on a common circular orbit, and we have designed a higher orbit for accomplishing this phasing rendezvous. So what we will look at next is essentially the same problem, but the transfer orbit OT will not be a higher orbit. Instead, it will be a so-called lower orbit. All right. So in this case, the size of the transfer ellipse will be smaller than the original orbit on which the two spacecraft are moving. Okay, so this is figure 2 on page 7 of your notes, part 5. So this is the initial orbit on which the two spacecraft are, and still the chasing spacecraft S1 is lagging the leading the target spacecraft by the same phase angle beta, and the transfer ellipse that we have designed is an inner orbit, so that point A is the apoapsis of the transfer ellipse OT. Okay, and this point B here is the periapsis, or the close point of OT with respect to the focus. Alright, so what we will do now is exactly the same analysis. Okay, we will assume the same things, that let S1 cover K periods of OT before it rendezvous with S2 at point A. Right? So after K periods of S1 on OT, they will both S1 and S2 will be at the same common point A, at which point again the spacecraft S1 will be transferred back to OI, completing the rendezvous. Okay, so the wait time, delta T wait, again is K, which is an integer, times PT. Okay, and PT is what we are trying to find. Now during this time, the angle covered by S2 is again the same, right? It has to first go through this angle at least, right, to get to A, and then maybe it covers an additional Q orbits, just like we had before. So the angle covered is 2 pi minus beta plus 2 pi times Q. It's the additional Q orbits. So we will equate that to as before, speed times time, right? The speed is ni and the time is k pt. So we have exactly the same equation, okay, as before for this lower transfer. So let me call this problem a lower transfer or a lower phasing transfer. All right. So we can solve this equation right here to get the same expression for pt as before. Okay, pt is 2 pi q plus 1 minus beta over ni times k. Okay, this is equation 17 on page 8 of the notes. Now, so where is the difference? The difference is in the constraints on the integers q and k. So here again, they're still integers, right? But the difference is that if I look at the right hand side of this equation, and like I had before, this is equal to k times 2 pi times pt over pi. But the transfer ellipse is smaller than the original orbit, right? So pt is less than pi, and therefore this fraction is less than 1. Okay, so what we have is that this left hand side is equal to ni times k times pt, which is equal to 2 pi times k pt over pi, which is less than 2 pi k times 1. So from here we get that 2 pi minus beta plus 2 pi q is less than 2 pi k. Divide throughout by 2 pi and we get that q is less than k minus 1 plus beta over 2 pi. This is the constraint between k and q, which is different from the constraint we had for a higher transfer. Alright, so let us draw that line again and let this be k. So this point is k minus 1 to the left, and then we add beta over 2 pi to that. So this point, this is where somewhere where k minus 1 plus beta over 2 pi is, and we are saying that q should be less than this value, so this is the range for q. And since q is an integer, this is now the maximum value q can take, right? It cannot be to this side, so q can never be k. All right, the maximum it can be is this value, okay, because this is not an integer. So q max is k minus 1. This is the constraint for a lower phasing transfer. Okay, all right. So what you can do is you can in equation number 17, which is the expression for pt, it's right here. So over here, if you substitute q is equal to k minus 1, look at the special case. So like in the higher transfer case, look at the special case in which q is equal to q max here. So q is equal to q max is equal to k minus 1, and we get that p transfer for q is equal to k minus 1. So that special case turns out to be pi minus, as expected, since pt is less than pi, minus beta over ni k. Okay, this is the special case scenario for the lower transfer, okay, for q is equal to k minus 1. And to finish this case, we look at delta v, and delta v is exactly the same. The expression basically is exactly the same as for the higher transfer, because the symmetry still holds. The spacecraft goes from OI to OT and then back from OI to OT to OI, and the delta v's are the same. The expressions for the velocities are the same. So I have mu over r. This time the circular speed is greater than the elliptical speed, right? Because the elliptical is a smaller orbit, minus speed of the ellipse, 2 mu over r minus mu over at. and AT is found from PT, from Kepler's third law. Okay, so that's what delta V is. All right. To finish this section, we will do an example problem, and we will, analyze this whole thing in depth, because see, we have 4 cases, all right, for the same phasing rendezvous. Case number 1 is one in which we do a higher transfer. Okay, the transfer ellipse is bigger than the initial orbit, and within that case we have 2 sub cases. One was the special case in which q is equal to k, and the other case in which q is greater than k. All right, and the case 2 in which we use a lower or an inner transfer ellipse, and within that case again there are 2 cases. One in which the special case q is equal to q max equal to k minus 1, and the other case in which q is less than q max, which is k minus 1. All right, so here's the problem that we're trying to solve. We have a circular orbit of altitude 300 kilometers. Okay, and our target spacecraft S2 is leading the chasing spacecraft by an angle of 20 degrees. So that's beta. The objective is to do a phasing maneuver involving spacecraft S1 such that the rendezvous takes place at point A, and we would like to find the minimum amount of delta V. Find delta V min for this maneuver such that maneuver is complete in less than 10 hours. Okay, so you might be thinking why this 10 hours is important, right? So you remember this, there was no upper limit on k, right? How many orbits that you can cover on the transfer orbit. So by placing this constraint, what we are saying is that the number of orbits cannot really be infinite, because as you increase the number of orbits, the time needed to complete the maneuver will increase. So we are saying that put a limit on k such that the total time needed for this entire maneuver is less than 10 hours. All right, so now what we will do next is essentially explore all these 4 cases separately and try to see which leads to the best or the most fuel efficient phasing transfer. All right, so our solution begins by looking at case A, which is the phasing transfer involving a higher orbit or bigger orbit, and within this we have 2 cases. Like I said, case A1 is where q is q min, which is equal to k, and case A2 in which q is greater than k. Okay, so for q equal to k, we have the special equation number 11. So A1 PT equals PI plus the additional to cover out the phase KNI. Now of course, now Q has disappeared, but there is still K, right? And so we have a upper limit on the total amount of time, which is 10 hours. So let us just plot this function, right? PI is known because that's the initial orbit of 300 kilometers altitude, and that is also the semi-major axis, so you can use Kepler's third law to find PI. And if you look at page 11 of the notes, PI is 1.51 hours. Okay, and also while we are at it, for this case, delta V is equal to 2 square root 2 mu over r minus mu it. This expression we already have, minus mu over r. Okay, where at is given in terms of pt, okay, which is right here. So what we are going to do is we are going to plot 3 figures. The third figure will involve total delta t for the maneuver, right, which is delta t weight, and that is nothing but k times pt, because the rendezvous takes place after k orbits of the transfer ellipse. Okay, so the solution is given in terms of three graphs. This is figure 4, figure 5, and figure 6 for delta t weight. And in each of these figures, look only at the solid line, okay, the solid bold line, in which we are looking at the higher orbit, because case A is the higher transfer. Okay, and as you can see, figures 4, 5, and 6, each of those three figures correspond to q equal to k, which is the case A1, for the higher orbit phasing. All right, and what we have done is, in each of these figures, the value of k has been varied from 1 to 10 in increments of 1, since k is an integer. Okay, so anything between 1 and 2 is meaningless, and so we are taking 10 possibilities, and we'll see what works. All right, so let us first look at figure 4 in your notes. This figure has, on the x-axis, it has k, and on the y-axis it has pt of the transfer ellipse, which is the period of the transfer ellipse. Okay, and the solid line corresponds to the higher orbit phasing maneuver with q equal to k. All right, so you see that as when k is small, the period of the transfer ellipse is quite high. Okay, and this dotted line you see in that same figure is the period of the initial orbit. Okay, this is pi, the thin dotted line, not the bold one. So what we are seeing is that when k is small, meaning that this rendezvous must occur in just one go around of the transfer ellipse. Okay, so that is kind of demanding, because it depends on what the phasing angle is, what the phase difference between the two spacecraft is. If the phase difference between the spacecraft is large, it means that the periods of the two orbits, the initial and the transfer orbits, must vary by a lot, right? Because we need to close out that phase angle, so we need to create a differential between the periods of these two orbits. So for large phase angles, there must be a relatively big difference between PT and PI, especially if this maneuver is to be completed in just one go around of the transfer ellipse. So that's what you see. As K increases, the period of the transfer ellipse goes down for this maneuver. And so the way you interpret that is that as K increases, the phase angle closes out gradually, okay, per orbit or per go around of the transfer orbit. So it kind of reduces the load on each go around of the transfer orbit. All right, since you have more time, right? So you gradually close out the phase angle, and therefore the difference between the initial orbit and the transfer orbit need not be as much. Okay, and that's what you're seeing, that the period comes closer and closer, the period of the transfer ellipse comes closer and closer to the period of the original orbit. And that translates directly into figure 5, which is a plot of delta V versus K for fixed Q equal to K. So again, in figure 5, look at the solid curve, which corresponds to the higher orbit. Okay, so what you're seeing is that when K is low, for example, just pick K equal to 1, the delta V is more than 2.5 kilometers per second. Okay, so that's huge. So what we are saying is, that the phase angle is large, so we need to create a big differential between the initial orbit and the transfer ellipse. And so that big differential between those two orbits results in a large delta V, right? But as you increase K, which means that the phase needs to be closed out gradually, so the differential needs to be small, because you will be closing out the phase gradually, one orbit after another. And so the delta V needed when K is equal to 10 reduces to less than 0.5 kilometers per second. Okay, So that's how we interpret figure 5. Now this reduction in delta V comes at a cost, right? And that cost is that the total time needed for the maneuver, which is k times period of the transfer ellipse, must increase, right? Because you're increasing k. So that's what you see in figure 6. Again, look at the solid bold curve which corresponds to the higher orbit phasing transfer. Then there is this thin dotted line which is the cutoff, right, at 10 hours, and that's the limit that has been placed on this problem, that the amount of time needed for this maneuver should not exceed 10 hours, and that immediately puts a upper limit on k. All right, so I have identified k equal to 6. Okay, if you look at the figure at k equal to 6, it exceeds on the solid line, it exceeds the cutoff. Okay, so k cannot be equal to 6. The maximum k can be is equal to 5, and we want k to be high, right? Because what we have seen is that higher k means a lower delta V. Okay, so that's how we read these three charts for the higher transfer orbit, and based on figure 6 and figure 5, we are going to say that the cutoff is 10 hours, so k must be 5, and the corresponding delta V at k equal to 5 is equal to 0.82 kilometers per second. This is noted on page 13 of your notes. Okay, so from here we conclude that k is equal to 5. Corresponding delta V total is 0.82 kilometers per second, and the time of the maneuver, total delta T, is 8.97 hours, and that is good because it is less than the 10-hour limit that has been placed. And the period of the transfer ellipse for k equal to 5 and q equal to k is 1.79 hours. What we will do next is look at case A2, in which q is greater than k. Okay. Now we need to fix k in this case. So what we will do is we will take hint from case A1, and we found that k equal to 5 is the optimal, right? Because it also satisfies the constraint of 10 hours. So in looking at case A2 now, we will set k equal to 5, and we will vary q from 5 to 10. From 6 to 10, since q is strictly greater than k. So that's the variation we will look at. Now, if you look at figures 7, 8, and 9, those three are the figures that correspond to variation in q. Okay, so the x-axis is q, figures 7, 8, and 9. And once again, in looking at these figures, concentrate only on the solid lines, because the solid line corresponds to the higher orbit transfer. Okay, so figure 7 looks at the period of the transfer ellipse versus q. Figure 8 looks at delta V, and figure 9 looks at the total time of transfer, which is k times pt. Okay, so you may think that k is fixed, so why is the total time for the maneuver changing? Well, it's changing because q is changing, so pt is changing. Okay, so pt, you will see, is a function of k, q, and pi. So this guy is fixed. Alright, so this is fixed, but now we are changing q, and that's why pt is changing, which means that's why the total time of the maneuver is changing. Okay, Now, the important thing to notice here is in figure 8, what you're seeing is that as Q increases from 6 to 10, well, I have actually shown 5 there as well, I shouldn't have. So just focus on from 6 to 10, okay, and figure 8. So when as Q increases, delta V is increasing, and that's not good news, right? So we can stop looking at this case right away, because the minimum delta V corresponds to Q equal to K. And what figure 8 is telling us that if I increase Q to be more than K, then delta V starts increasing. And our objective was to find the optimal delta V, right? The question that we must answer is, why is this happening, right? Why is delta V increasing as we make Q larger and larger compared to K? And the answer is the following. So what we are saying is that for a fixed K, and of course fixed Pi, as Q is increased, PT starts increasing, right? Because delta V is increasing, which means that the difference between the two orbits is increasing and the transfer ellipse is getting bigger and bigger, okay? So why is that happening? Let's draw a picture. This is OI, right? And this is the transfer ellipse. What we are saying is that this is S2 and this is S1 at the beginning, right? What we are saying, well, let me also put in the expression for PT, general expression for PT that we had found is the same expression for all cases for general Q and P, or NIK. Alright, so that's PT, equation 7 or 11, whatever you want to look at. Now, we are saying that we are going to fix K, okay? So the spacecraft S1 can only do 5 orbits of this transfer ellipse, OT. But during that same time, we are saying that S2, let us look at the case of Q equal to 10, okay? So we are saying that in the time that S1 covers 5 orbits of OT, S2 must first cover this angle and then do 10 additional orbits. Q is equal to 10. Now when is that possible? That is possible only if PT is large, right? S1 will have to be on a much bigger orbit so that in the time it takes to do 5 of those orbits, S2 is able to complete 10 of its own orbits. Okay, so that can happen when PT is large. PT is large meaning OT is large, so there's a big difference between these two orbits, right? And so the delta V that will be needed here for this transfer is going to be big, right? So as you keep increasing Q, this difference between the two orbits is going to increase further and further, demanding more delta V, right? So that is obviously not desirable, and so we would like ideally to keep Q as close to K as possible. So moral here is, for low delta V, keep Q close to K, right? Otherwise you are creating a difference between, or distance between those two, the transfer orbit and the initial orbit, thus pumping up delta V needed. Alright, so that completes the analysis of the higher transfer for this case, right? What we have concluded is that this still is the optimal answer that we have so far. Alright, so now to cover all our bases, we will look at case B, which is the same phasing maneuver but using a lower orbit, okay, and see if we can do any better than what we have found so far. So far our optimal answer is that the time of maneuver is going to be about 8.97 hours, and the amount of delta V that will be needed is about 0.82 kilometers per second, and it will involve 5 orbits of the transfer ellipse. Okay, so that's the answer we have so far. Alright, so next let us look at the lower transfer orbit case. And that's what it looks like. This is the focus, S2, S1, rendezvous intended to be at point A, and the phase angle is 20 degrees. Alright, so now this is case B. Again, there are two sub cases. B1, in which Q is that special case, Q is equal to Q max, and the maximum value it can take is K minus 1, and B2, in which Q is less than K minus 1. Okay, so I'm going to immediately rule out this case, okay, for the same reason as case A2, because when Q is less than K minus 1, it means we are creating distance between K and Q. The closest Q can be to K is K minus 1, right? The moment it becomes K minus 2, it goes farther away, and it means that there's more distance being created between these orbits, and again the delta V is going to increase. Okay, so again we will revisit figures 4, 5 and 6. Now for case B1, again we have the equations, special equations for Pt equal to Pi minus beta over Nki, and delta V, I have that expression, is mu over R minus the V transfer ellipse 2 mu over R minus mu over AT. Here you already have these expressions. So with these expressions, again revisit figures 4, 5 and 6 and vary K from 1 to 10, but now start looking at the dotted lines, okay, because the dotted lines correspond to the lower transfer, lower orbit transfer. Alright, so we see very interesting results here. If you look at figure 4, the period, of course, is less than, the period of the transfer ellipse is of course less than that of the initial orbit, which is clear from this equation, right? Pi minus beta over Nki. So the fact that the periods are close to each other is a good indication, and it bodes well for delta V, right? So periods being almost equal means that there's very little distance between those two orbits, and that is confirmed in figure 5 when you see that the delta V is the highest delta V for the lower orbit is less than the lowest delta V for the higher orbit, right? So just hands down, the lower orbit transfer is much more fuel efficient, okay, than the higher orbit transfer. So this is the most optimal case. Now of course, as K is increasing, for the same reason as for the higher orbit, the delta V goes down, right? Because the phase is closed out gradually over several orbits as compared to just closing out the phase difference in just one orbit, right? So the delta V goes down, but of course the price to pay again is given in figure 6. The price to pay is that the transfer time, total time for the maneuver, will increase. So we compare that with the cutoff, and as you can see that for K equal to 7, the lower orbit transfer exceeds the cutoff. So K max that we can have is K equal to 6, since K equal to 7 exceeds it. So these numbers I have on the board here is for the higher transfer, and these are for the lower transfer. Okay, K equal to 6. The corresponding delta V for K equal to 6 is, since K is equal to 6, Q is going to be equal to 5, right? Because we're looking at the special case at which Q is Q max equals K minus 1. Delta V is extremely low, 0.05 kilometers per second. which is about 50 meters per second, right? That's a very small number. And the total time of maneuver, delta T maneuver, is 8.96 hours. Very interesting. Look at these two, compare these two set of numbers. The time of transfer is about the same, right? But look at the delta V. In the same time, for the higher transfer I need 0.82 kilometers per second, whereas for the low transfer I need 0.05 kilometers per second. Okay, so that's a huge improvement for no time lost, right? There's no additional time needed, and both of them are meeting the constraint of 10 hours. So as you can see, for this type of problem, and I'll comment on that soon, what type I'm talking about, but for this type of problem, the lower transfer is much more fuel efficient. Okay, all right. So to complete the analysis, anyway, I mean, I already crossed out case B2, but if you just look at figures 7, 8, 9, those represent case B2, and the Q is varied from 1. I could actually have varied it from 0, but it's varied from 1 to 5. I have fixed K at 6 because that's the optimal we found. And as you can see from figure 8, the delta V starts increasing as Q moves to the left, right? With the broken line. We are doing the lower orbit transfer. So again, look at the broken solid line. I'm sorry, the broken bold line. And as Q moves to the left, meaning there's increased separation between Q and K, delta V increases, and so that is crossed out. All right. So our optimal answer is that the optimal delta V that we have found is 0.05 kilometers per second, and it must be a lower transfer involving 6 go-arounds on the transfer ellipse, and in the same time the target spacecraft completes 5 go-arounds on the original orbit in addition to the phase angle 2 pi minus beta. All right. So there is one last thing that we need to mention, this distinction between the higher transfer and the lower transfer. All right. So what we found in this example problem is that for this phasing rendezvous maneuver, the lower orbit transfer was much more fuel efficient than the higher orbit transfer. And the reason that was true is that the chasing spacecraft was lagging behind the leading spacecraft. Okay, so that's not true always. What the problem we looked at was the one in which S1, which is our chaser, was lagging behind S2. Okay, in this case, we just saw that the lower transfer makes more sense. Why is that? Okay, the reason that is so is because S2 is already ahead of S1, right? It must meet S1 at point A, so it has lesser distance to travel to meet S1, to get to point A, right? So it makes sense to transfer S1 on an orbit which is faster, because it needs to cover a greater distance to reach point A, right? So in the time that S2 reaches A, S1 will reach there as well, being on a faster orbit, despite the fact that it's lagging behind S2. Okay? So that's why when chaser lags target, lower transfer is optimal. in terms of delta V. So if I turn this thing around now and say that the chaser leads, the chase spacecraft leads the target, then it's ahead of it already, right? So it needs to travel a lesser distance, so it needs less amount of time, right? So for them again to meet at a common point to which the target has a longer distance to cover, the ideal situation is to increase the period of the chaser, right? So that it has to it has some additional distance to travel so that they both meet at a common point in the future. Okay, so when the chaser leads the target, we haven't derived the equations for this, but it's almost trivial to do that because you know the entire procedure now. And so you basically follow the same steps, right? Compute the time of maneuver, compute the angle that the target must cover during that time, and you have the speed, and so distance is equal to speed times time, and that gives you pt. But anyway, so the final point here is that when the chaser leads the target in phase, then the higher transfer you will see is more optimal, okay. All right, so thank you very much. That concludes the our section on makeup lectures, and so now you have all the material that is needed for the final exam. There will be no more lectures posted on YouTube, and all the notes are up on Sakai except the one on interplanetary transfers that I completed in class today. So those notes will be up tomorrow for your benefit. You already have your class notes if you attended the lecture. Okay, so the supplementary notes that I write will be uploaded on Sakai hopefully tomorrow. All right, so thank you.